So we could start every year. We have a math sciences talk, and some years it's something like biostatistics or data science. And it's actually been a while since we've had one about pure mathematics, and so we thought we might have one this year. And we're really fortunate to have our speaker here today, who is Peter Sarnak from Princeton University and the Institute for Advanced Studies in Princeton. And just a little bit about Peter: he received his bachelor's in 1974 from the University of Witwatersrand, which is in South Africa. He got his PhD in Stanford in 1980. He's had positions at Sarnak, at Institute at New York University, Stanford, the Institute for Advanced Studies at Hebrew University, Caltech, Princeton, and now again at the Institute for Advanced Studies. And he's currently a professor at the Institute for Advanced Studies and the Eugene Higgins Professor of Mathematics at Princeton University. And like I said, we're really fortunate to have him here. I've known Peter for about 25 years, and he is always interested in what anybody is doing in mathematics. And he's very engaging, and I hope many of you will get a chance to talk to him later. So today he's going to give us a talk on navigating PU2 with Golden Gates. Peter.
Thank you very much. It's a great pleasure. Sorry to disturb your breakfast. Please feel free to eat as long as you watch. So I've chosen this topic because I think it's of quite wide interest, and it's even got some potential real applications, and I will try and introduce it with some practice problem and then explain what's behind the mathematics which makes it work, at least at a high level. So let me start with a practice problem. It's a problem about the best rotation in the group U1. So the group U1, which is just the complex numbers of modulus 1, so numbers, non-zero numbers, z in the complex numbers, such as zz bar or zz star. I'll use star for, once I get to a matrix, the complex conjugate transpose. So the non-zero complex numbers form a group under multiplication, and the numbers of modulus 1 are a compact group under multiplication, and that's just the unitary group U1. You can also think of it as the reals modulo the integers by simply taking the homomorphism, which takes a number theta to e to the 2 pi I theta, and that takes you into the circle, and addition becomes multiplication. So it's a compact group. It's something extremely simple, but the problem that we're interested in, and there will be some number theory, that's my main interest in the world, and my claim is number theory is the most applied of all fields, and I hope to convince you today, especially with the modern computer. So we look for the best generator of this group, topological generator. So suppose I take a rotation R alpha, which is just in the theta variable. I take theta to theta plus alpha, and then I iterate that rotation. So I repeat it, and I get R alpha to the j equals 1 to up to k, and I repeat that forever. Each R alpha to the j is a new rotation, which in the coordinate theta is just the rotation given by j alpha, all up to integers, so maybe the fractional part of j times alpha. If alpha is irrational, then these powers of this rotation will go around the circle, I'll show you a picture in a minute, and become dense. And so the closure of this rotation would be the whole group. And we are interested in the problem which is the best generator of this rotation group. What rotation is the best in the world? So best always requires what you mean by best. And in this case, I'm going to look at these rotations. There'll be points, if I look at the first k powers, there'll be k points in the circle, and I want them to fill out the circle, to cover the circle as evenly as possible. So if alpha were rational, I would just go through, say that alpha were 1 over q, I would just go over the numbers j over q, and they would never become dense. But if alpha is irrational, eventually we'll get close to everybody. And I'm looking for the rotation which does this optimally. And one way of measuring it is, let's look at the biggest gap. So this LK alpha is the maximum over all intervals in the circle, such that the interval contains no points from the first k rotations. So it's a maximum over the length of I contained in the interval, such that I intersect these k rotations, the first kth powers, is empty. Clearly, if I put down k points in a circle I've normalized the circle to have length 1, there must be at least, if I only put down k points, there has to be a gap which is at least 1 over k. So this k alpha must be greater or equal to 1 over k. So I want to try to keep that number, lk alpha, or k times lk alpha. So this is supposed to be a picture, and I think I can make it better by doing that for a second. Well, all right, you can see these rotations. The one on the left, I'm sure you all know that the best rotation is the golden ratio. That's where I'm going. And the one on the left is the golden ratio, and you can see these gaps for k equals 45. The gaps are these yellow, blue, and red. They are, it's not completely obvious, but if you take these fractional parts of J alpha and you look at the gaps between the first k of them, they only take 3 possible values. That's a non-trivial fact. It's not very difficult. And here you see the 3 values. On the other hand, on the right circle, where you see just part of it, the rotations are much worse distributed. They become dense. And that corresponds to an irrational number like pi in these coordinates. So you can see the golden ratio doing much better. So how can we measure this, and how can we make it a theorem that the golden ratio is the best? So I think I need to go back to this full screen mode. And there's a beautiful theorem really going back to Vera Schoch's thesis in the 50s and later proved in this form by Ron Graham and Van Lint. And that is, if you take k times lk alpha and look at the lim sup, you're trying to make that number as small as possible. As I explained, it's got to be greater than or equal to 1 once I multiply by k. If you try to keep that number as small as possible, for most alphas, this number k times lk alpha will go to infinity, the lim sup. But the best you could ever do is keep it as small as 1 plus 2 over root 5. That's the smallest or the best equidistributed for all k. Notice we do for all k. I repeat, if I were to take k equal to q and I chose alpha to be 1 over q, then I could divide the circle up exactly into q equal parts. But I want a number alpha which works for all possible k's simultaneously, and that theorem here says that you can never do better than 1 plus 2 over root 5, and the best number that you can choose is 1 plus root 5 over 2, which is the golden ratio. And if you want to navigate, I'm going to be doing the same thing with 2 by 2 matrices. This whole lecture is about 2 by 2 matrices instead of 1 by 1 matrix. If you want to do the same with 2 by 2 matrices, we'll be interested in this navigation problem. Here the navigation problem is, I would give you a small interval and ask you, from all the j alphas, j up to k, which is the first j which enters this interval? Can you find that efficiently and quickly? And the answer is, if you use the golden ratio there and make a few computations, you'll find that you can use the oldest algorithm in the world, and still the best algorithm in my view, Euclid's greatest common divisor, GCD. It's an algorithm to compute the GCD of 2 numbers, which it does in log of the number of digits of the numbers steps by taking remainders in the Euclidean algorithm. And if you apply that to this golden ratio, you actually can not only show that this golden ratio is the best generator of the rotation, but you can navigate, you can find your position. If you give me an interval in which you want to find the smallest time in which I get into that interval, you can find it very quickly. So that's our practice problem, and notice that the solution is like all interesting. Everybody loves the golden ratio. It comes up here because its continued fraction is very special. All right, So our problem is to try, and this is the rest of this lecture, is just to discuss this problem for 2 by 2 matrices. So the unitary group are 2 by 2 matrices, G, such a G, complex entries, such a G, G star is complex conjugate transpose, equals identity. That forms a group. And you put SU2, indicates special unitary group, is just the statement that the determinant of the matrix is 1. Very close to SU2 is the projective unitary group, which is just the 2 by 2 unitary matrices divided by the scalar matrices. I'll interchangeably use SU2 or PU2, don't worry about that. Okay, now we have a much more complicated group. It's a 2 by 2 matrices, it's a compact group. The matrices lie in a compact set, so you can use the Heine-Borel theorem to see it's compact. It's a topological group, there's a topology, and let me tell you what the distance, there's a distance which is very friendly to the group. It's called the bi-invariant distance. So if you define the distance between two unitary matrices, special unitary matrices, to be 1 minus the absolute value of the trace of G star H over 2, this is the distance squared between G and H. You can check that's a distance function. And if you compute the distance between G and H and multiply on the left by an arbitrary element Y in the middle line there, or you multiply on the right by an arbitrary element Y, you don't change the distance. So this is the unique, up to a scalar, bi-invariant metric. So in the circle, we didn't say about what topology we put there. We just have the circle, and I was talking about intervals. There was only one natural measure and one metric to use. This is the only natural metric to use on the group SU2. There's a measure on the group, which is an invariant measure. So it's a volume form on the group such that we normalize, it's compact, the volume of the group to be 1, and it's left and right invariant. So the volume of G times any set A is the volume of G times A on the right or the left is just the same as the volume of A. So when I measure sizes of sets, just like I was doing in the circle, we're now in this situation that our group is not abelian anymore. And that's the big change here. The matrices don't commute, 2 by 2 matrices. And this, the question we want to do is, what are the best topological generators? What's the analog of the golden ratio in this setting? And again, I'll have to define best, and the answer here is going to be much more complicated. Now, I was introduced as giving a pure math talk, but I'm going to explain to you that these golden gates, so this is theoretical quantum computing. If anybody ever builds a quantum computer, these gates will be in every machine. This will be what replaces not and in a classical computer, I claim. And I want to explain that just very briefly. So in classical computing, all classical computing are based on Boolean functions, for example, the various models. And the fact that you can make a computer is based on the fact that you can make a circuit where you can feed in a Boolean variable x1, x2 bits, as they are called, which are either 0 or 1. And you have a function from 0, 1 to the end to 0, 1, and you want to write it down as a circuit. And writing it down as a circuit means that you must be able to make certain operations if you want to compute anything, if you want to do anything. So you should be able to compute the negation of a variable, change one bit from a 0 to a 1. That's this not x, which is often written by that in engineering books, by that diagram, circuit diagram that you see. I guess if I were to try, no, let me not try point, I'll be wasting. And. So if we have not and and, we can write down any Boolean expression in terms of these two operations. And for example, if you want to write not x1 and x2 and not x3, that's the circuit that would achieve it. Now, the theory of complexity is concerned about making the shortest circuit to achieve a particular function. That's very difficult. I'm talking about a much more basic thing, is how do you build the hardware of a circuit? And it's a fact of life that you only need not and. You could use other binary operations to get all expressions. So these are universal classical gates, as they are called. In the quantum world, the only change at this theoretical level, so the big challenge of modern quantum computing is to build a gate efficiently and be able to reproduce it in the laboratory. But at the theoretical level, a quantum bit, is no longer a 0 or 1. A qubit is a vector in C2 whose length is 1. That comes from the interpretation of quantum mechanics in terms of probability. So I don't need to go into that, but we have a vector which, when you measure it, it will collapse into a state. But before you measure it, it's just a vector. The one qubit is just a vector in C2, whose complex as a vector in C2, its length, absolute length squared, as you can see, is usual in complex numbers, is 1. And if you want to write a program with a quantum computer, you must be able to take your bit, your one qubit, and move it to another qubit, just like we did before. We had a 0, 1 was a classical bit, and we could switch from on and off. This whole lecture is about the operation, which is the same as switching not. That operation. But there's something fundamentally new here, because the gate is going to be an element which preserves the length. So in quantum mechanics, all dynamics is unitary. So we're going to have a unitary 2x2 matrix that you build in the laboratory, a gate, which will take you from a vector of length 1 to another vector of length 1 by multiplying just by this matrix. So in physicists like this bracket notation of the Dirac. So they don't write vectors, they write /x bracket. It's very hard to read if you're a mathematician, but it's just a vector x goes to g times x. That's what that quantum circuit is. This notation, I think, was introduced by Feynman, who first raised the possibility that a quantum computer might be something interesting. The unitary group, explicitly as I've mentioned it, is a 2x2 matrix group with complex numbers. G star, I repeat, is the complex conjugate transpose. We're looking at matrices such as G star equals I. That's our group. And in terms of these coordinates, alpha, beta, if the determinant is 1, this will be useful to us. Then our entries in our matrix G are alpha, beta, minus beta bar, alpha bar, where alpha squared, modulus alpha squared, plus modulus beta squared is 1. So it's a three-dimensional real group, this SU2. And that's our basic gate. We're going to ask, what's the best gate you can put in the world so that you can do like what I did in one dimension with the rotation? Now, of course, if all you had was 1 bit, you wouldn't have much of a quantum computer. In classical calculations, you have n bits, and you had that operation which allowed you to change x to not x, and then you were able to take any 2 bits and talk about x and y in 2, without interfering with everybody else. That's what's very difficult in quantum computing. So I'm only talking theoretically. So the actual quantum computer will involve n qubits, which is the vector space of dimension 2 to the n, which is this vector space that we have of dimension 2, tensored up n times. And in order to write down a universal set of gates, just like we had not and, we need here something which will take in 2 qubits. So that's a vector space of dimension 4, and this XOR gate is a standard one that's used. Don't look too closely at what the formula or the circuits are. I just wanted to show you that it's actually, if you open up any basic quantum computation, theoretical quantum computation book, you'll see all these matrices, and you'll see these kind of circuits. Now, it's well known, and this is an exercise in just matrices, that if you have this XOR gate, which is a gate which involves 2 qubits, but you're allowed to take any 2 qubits and make this operation, and you have all the rotations in U2, SU2, then you can write down any matrix, any unitary matrix, as a product of these. The product of these will be the circuit. So if you want to make a gate set for computation, and you're willing to use XOR, I'm not saying XOR is the universal one, and I don't have the answer for the 4x4 matrices, but there's a new problem that emerges, and that's just about the 1 qubit. And that's this operation of going from a matrix to G times a matrix. Just to make that clear, there's a very big difference is in the case of a classical computer where you are just 0 or 1, the operation is just switch on and off. Here, our whole set of vectors is the set of vectors of length 1. It's a continuum. A computer can't work in a continuum. You can't build a continuum number of gates. So the question now is which gates, say you want to give me 2 or 3 gates in SU2, which can be used to approximate any element in SU2 by writing a short circuit, meaning products of those rotations, and that should cover the group SU2 just like the golden ratio covered the circle. That's our problem, and that's the problem of the best gate set, the best universal gate set, the thing that replaces not. So I won't talk much except a few words at the end about 4x4 matrices. We'll stick to 2x2. I claim that no human really can work with bigger matrices anyway. You can ask a computer to multiply 4x4 matrices, but we can do scalars and we can do 2x2. It's a good thing linear algebra doesn't restrict us to just 2 dimensions. It would be a boring, it would be rather useless. But if you think of Gaussian elimination, or you see what I'm doing here, everything you do is you always go row elimination, you do 2 at a time. That's all our mind can think of is 2x2. So we'll stick here just to this question. There's a typical, if you open a book, this is a computation for 3 qubits of the Fourier transform written in terms of these matrices here. Now, people in the subject, seems like you can see the impact on physics. It seems in physics you get famous if you have a 2x2 matrix named after you. So there's the Hadamard matrix, which is that unitary matrix over there. And if the determinant's not 1, then it's in PU2. Excuse me there. There's the Pauli 3 matrices, which are rotation really by the x, y, and z axis. There's phase matrix. And this finite set of matrices here, 1, 2, 3, 4, 5 of them, if you multiply them, you will get a finite subgroup of SU2. I'm going to return to the finite subgroups of SU2. They're going to play a very important role. The finite subgroups of the rotation group are these rational numbers, which we eliminated immediately on the first slide. But here we have some very interesting finite subgroups of SU2, and they must play a role. And this particular group is order 24 that all quantum computing people love. And it's called the Clifford group. There are many ways of other ways of defining it. We'll see in a moment it's the symmetries of the cube. That's a finite group. So if your quantum computer could, if the gates that you used were just this 24 gates, because that's a finite subgroup of SU2, you're not dense. You will not be able to make your quantum computer do anything that a classical computer can't do. It's a separate question whether a quantum computer is actually better. I'm a skeptic, but that doesn't matter. This is, so to get the power of a quantum computer, you must be able to get to all rotations and be able to approximate any rotation. So a finite subgroup by itself is not good enough. But we do start with a finite subgroup. I've got to make my usual joke here. My dream is that they'll name the identity element after me, because then I'll be in every group. It is a funny subject. They're just naming individual matrices after people. Okay. In order to get a dense set of 2x2 unitary matrices, say in SU2, you have to throw in, just like we did in the circle, we threw in this irrational rotation by the magic golden ratio. So in this quantum world where people were developing this in the 90s, since the 90s, for some reason this matrix, and if you go to the IBM little program that does quantum computation, you'll find this T matrix. They love this T matrix. I don't see anything canonical about it. I'm going to replace it by something much better as we go along. But they knew that they have to add another matrix. You have these finite groups, the Clifford group. To be dense, you better throw something that somehow doesn't get you out of that subgroup. And what element would you throw there so that you have the beauty of covering the group optimally and navigating at the same time? So there's this square root of the phase matrix, T. It's order 8. So all these elements are finite order. But do not be fooled. If an element's a finite order, just simply means its powers form a finite subgroup. But if I, of course, take T and I multiply by the Hadamard, I might get an element of infinite order now. So it's very easy to see this T matrix, as it's called, or the pi over 8 gate. When you throw that as into with C24 and look at all the words you will form, all the circuits you would form out of those matrices, that will be dense in SU2. That's not difficult to show. What's not clear is how well those cover the group. And the computer scientists, Klashnikov, Maslov, and Moscow, about 10 years ago, asked, so there were libraries of these, and people doing quantum computing would try approximate arbitrary rotations with these, with a T matrix. But they asked the very clear question and answered it very clearly, is what 2x2 matrices do you get if you take the Clifford group and then add this T and then start multiplying all those? And as you can see, that's a question in number theory, because you've got roots of unity there. You're multiplying. When you multiply two matrices, you multiply row and column, you've got multiplication and addition. So you're probably getting entries there of 2x2 unitary matrices whose entries are in a ring in a number field. And they discovered that, and that was a remarkable thing, because in the theory of automorphic forms, David said we know each other for many years. In automorphic forms, we work with these groups all the time. But we say, take all the matrices which are 2x2 integer matrices. We don't take the generators. In our theory, we define them globally, and then somebody else comes and says, well, I can give you a set of generators for this group. But these guys are just computing, and they're trying to navigate in SU2. They choose the generators first. It's very unlikely they would get something that's of an arithmetic significance. But that's what they discovered in their own language. They actually identified what the 2x2 matrices, what entries in what ring, in what number field they lie, and that opened the door for them to start making all sorts of conjectures, all of which we'll be able to answer but that's the miracle. The Clifford and T is an arithmetic group in fancy language. And given that I told you that XOR, so now that's the Clifford and T is dense in just the SU2, and then XOR is this thing that takes two at a time. That's a completely general universal gate set. So if you ever want to build a quantum computer and they want to know what to build in the laboratory, what rotation, this would be enough to make any universal computation. Not optimally, but that would be enough. Okay, I got interested in this because I knew about this group. I had written a paper with Lubotsky and Phillips many years ago about the best rotations. We didn't know about quantum computing, but we had some other problem where we were saying, here are the best rotations in three dimensions or in SU2. And when I saw this example of theirs, I recognized this is a special case of what we were doing, and we have a whole theory, and that will lead to what I'll say here. All right, I'm going to explain these finite groups in terms of Platonic solids. I remind you, which is anyway a very important fact of life, that this SU2, which is a simply connected group, is the double cover of SO3. Let me explain that very concretely here. So the 2x2 matrices, as we've seen of determinant 1, are alpha, beta, minus beta bar, alpha bar. And if I look at the matrices in SU2 of trace 0, so they have to be of the form, they have these three coordinates, x2, x3, x4, where those are real numbers, and the trace of G is 0, and the sum of these three squares is 1 for the trace 0 determinant 1 elements in SU2. And then if I look at x2, x3, x4, which is a vector in R3, and I conjugate by taking G star, this trace 0 matrix, times G, the trace won't change, so that now SU2 acts on R3. It preserves distance, as you can check, and the map, and it induces a rotation in 3 dimensions. And this map from SU2 to SO3 is a double cover, and SO3 is not simply connected, and SU2 is topologically, I'll use this all the time, is the 3-sphere, is simply connected. So you could take those 24 rotations that these guys like, the Clifford group, and see what rotations they give in 3-dimensional space. And they're the rotations of the cube. All right, in this theory of quantum computing, there's a beautiful theorem from the 90s, which at least conceptually says that this approximation problem has a weak solution. It's called the Solovay-Kitaev theorem, and let me just say what that is, because it's very cute, and the proof is very beautiful. I can explain it with my hands. By the way, what's the time? So The Solovay-Kitaev theorem says the following. So this, before I give you the answer to these, what's the analog of the golden ratio? Suppose I give you two matrices in SU2. They don't commute, and they generate SU2. You have to work very hard to take two random matrices in SU2 and have them sit in a finite group. If you just choose them at random, they won't know about each other, and when you start multiplying, you'll get everywhere. That's not hard to show, but we don't know how well we cover the space. That's the difficult problem. And cover here means with words. Say I take A and B, and I take words with length. I just take A and then B and then A inverse and B inverse, and I just form all the possible words of all lengths and try to see where I get. In order to show that a quantum computer could simulate a classical computer, this is what the Solovay-Kitaev theorem is, they needed to show that there is an algorithm which allows me, if I have A and B, so you give me A and B which generate SU2, and you give me an arbitrary element in SU2, can I find a reasonably short word in A and B which gets to within epsilon of that? How do I navigate SU2 with an arbitrary A and B? So they didn't know which A and B to choose, so they say, you give me A and B, you secretly tell me they generate, I'll tell you how to navigate. So you might think, how do you do this? So they have a very beautiful idea. What they do is they start at the guy you want to get to, and they start to apply A and B. Now you don't know which to apply. And the point is I want a algorithm which is polynomial in the length to get close to the guy, not exponential. I don't want to go look at all words in A and B, exponential number of them, to see which is the closest. When I said these quantum computing guys had libraries, that's what they were doing. They were writing down the library of how the space is occupied with a T generator. So what Solovay and Kitaev say is, you told me that A and B generate, so that means if I just start doing A and B for some, like a drunkard, I just apply A and B and I wait and I wait and I don't know what I'm doing. But after some bounded number of steps, I will get within 1/10 of the identity. I want to get very close to the identity, that's what the problem is, but I can get to some fixed neighborhood of the identity. And then they use the exponential map from the tangent space of the identity, from the Lie algebra of the group to the group, to pull back this question to trying to navigate once I'm in the 1/10 neighborhood to get much closer. And then they use a very nice idea that if you take the commutator of two matrices which are near the identity, that commutator is typically much closer to the identity. So it's like Newton's method. Once they get close, then they can get close repeatedly by defining shells, and it's a very beautiful idea. And it's very general, and it allows you to get within epsilon of any guy in a polynomial in log 1 over epsilon steps in your generators A and B. The part that's, of course, not defined is the beginning part where you walk like a drunkard. That they can't control. You just have to wait till you get 1/10. So that's a theorem which in quantum computing at the very soft complexity class level says that a quantum computer can do what a classical computer can do at least. But for us, I want this optimally. This is an engineering problem, and we now got matrices with algebraic number entries. It's got to have a beautiful answer. So the problem, as I'll set it up here, is we have a finite group C. It could be the group of Clifford matrices. And then for a number of reasons, I want to add in one more matrix so that they become dense. I'll call that the T matrix, the miracle T matrix. But I'm going to assume that T squared is 1. I want to add something which, when I start making circuits, I apply something from C, and then T, and then something from C, and then T. I don't have to worry about powers of T. I could make T a finite order, not 2, but this is clearly, I think, the natural problem. So you want to throw in an involution so that they become dense, and the question is, if I give you a finite subgroup of SU2, what's the best T to throw in? And now and best will be what I've described now. So the number of circuits I can form, the number of words, and the T count is what's considered the expensive. I don't want to go into the application, but in the application, it's When you apply T, that's the expensive thing in the quantum computer. So we're going to form words inside SU2, which are of the form, I take something in the finite group, C1, I then apply T, I take something in, again, an arbitrary guy in the finite group C2, and I form these words, and I count how many T's there are. And clearly the number of words I can form, at most, is just combinatorially the number of words like that I can form where C1, C2 are in the finite group C, and where the T, I place them either, so there's the beginning and the end, and it's basically the cardinality of C to the power T is the number of words of length T. And if I want these words, just like in the circle, I want it irrational so that the rotations I get all distinct. I want all of these to be distinct because I don't want redundancy. And then the big covering problem is I want, if I look at all the circuits of length K here, which I've denoted by their cardinality by NF of K, so don't read that, it seems too complicated. I think I can just explain it in words here. I've got all these words of length K that I can form out of my finite group and the T. The T count is the complexity. So I have N of these rotations in SU2. How well could they cover SU2? What's the best we could ever hope for? Well, by just pigeonhole considerations, if I have N points in a space, if I have K boxes and I'm throwing N balls into K boxes, I better have more balls in boxes if I want to fill every box. So there's a lower bound here that if the volume of B, if I want to hit every ball of size volume B with respect to the whole measure, the volume of B times the number of points must be greater or equal to 1. Well, I can never ensure that I get into B, but I just don't have enough points. It would be fantastic if that's all I needed. If I could engineer it so that as soon as I have enough points, I hit everybody that I want to hit. But that's impossible. You even saw that with the rotation. That was the fact that was that argument I gave that L alpha K was greater or equal to 1 over K. So K times L alpha K was greater or equal to 1. The golden ratio achieves that, but with a slight, the constant is not 1, it's slightly bigger than 1. So the best we can hope here is that somehow we're going to do this cleverly, but we can't be, I don't believe there's any clever way of doing this filling up so that it would be absolutely as good as the golden ratio. But I want to point out to you what's called the coupon collector's paradox. If I throw N balls into K boxes, and I want to make sure each box has a ball, well, as I just said, I better have more balls in boxes to start off with. N better be bigger than K. But if N over K goes to infinity very slowly as you wish, basically, as long as you do it at random, you will fill every box. So throwing things at random, you might put 2 or 3 in the same box, or a bit more, but less. But doing things at random is good as long as this ratio goes to infinity. And it turns out that the golden gates, which is where I'm leading you to, the ones that do the trick, will do this because of some deep number theoretic features, because I secretly know that they're behaving as if I'm putting these points down at random. And so the optimal covering is up to the sense that, in the sense that not that the volume times this number that bigger than 1 already means I can cover, but the volume times a number must go to infinity, then I cover. That's covering at this finest scale possible. That's what I want of my words of length T. And then, of course, to be useful, I want to navigate. I want to be able, you give me a guide, so if you're ever going to run this and use this quantum computer, your program will call for some rotation, and then you'll want to say, all right, what's the best approximation in terms of these gates? Something like Euclid's algorithm. Can we run a Euclid algorithm in SU2? I should say that Euclid's algorithm is basically based on inverting a number, fractional part inverting, so you sort of know where to navigate. But when you're in SU2 and I give you rotations, it's not clear where to look. So this navigation is non-trivial. Okay, so what are the finite subgroups of SU2? I'm going to give you a golden gate for each of the Platonic solids. And Platonic solids are the tetrahedron, octahedron, cube, and the most interesting one, the icosahedron. The rotations which preserve these platonic solids are finite subgroups of SU2 or PU2. Those are the finite subgroups. So the Clifford group that they were using is not sacred. In fact, the best, as far as I can see, would be to use the icosahedral group, or the group which is the symmetric group, the alternating group on 5 letters. So the symmetry group of the tetrahedron is the alternating group on 4 letters of the cube. It's S4. That's the case that they were considering. That's a Clifford group. And the icosahedron has a group of order 60. I'm going to make a remark about these orders of these groups, which I'd never realized until Parzanchevsky and I provided these. So this is joint work with Parzanchevsky. You can find it in a recent edition of, I think it's called Advances in Mathematics, dedicated to David Kashdan. And these are a solution to this problem. So for each of these finite groups, and I think let me go straight to the most interesting one. Was it time? Well, the 2 interesting ones. The Clifford group. So you have the Clifford group C24, which I described, where what is normally added is that T-gate. Instead of adding the T-gate, we add this T-gate, which is an involution, which I call T24, and you add that involution together with C24, that will form a golden gate set. It will satisfy all the properties I want. Optimal covering, distinct elements, and navigation up to a point that I will end the lecture explaining. And then by far the most, the best, which maybe should be patented, is the icosahedron, where you have a group of order 60, the finite group of symmetries of icosahedron, and then you throw in this extra guy called T60, an involution, and you wouldn't be surprised to find that one of the entries, the 2 diagonal entries, involve the golden ratio. So there's a matrix you're adding there. The new group is now dense, topologically dense, and it's optimal in the sense that I described. That's the theorem of Parzanchevsky and myself. We make these constructions, and we call them golden gates. And there are only finitely many such examples. So if I give you the only finitely many interesting finite subgroups, I'm not talking about something called the dihedral group. So there are finitely many, there are 5 platonic solids. Each one of them gives me a natural finite subgroup in SU2. And then the question is to add in this magic involution, and there are only finitely many. There are other choices, but there are only finitely many. The number theory involved requires that the order of the group, the finite group, be a prime plus 1. So notice that 12, 24, and 60 are all a prime plus 1. If that was not the case, we wouldn't succeed. So I have no idea why that happened, but we were lucky because we use p-adic somewhere. And it could have been a prime power plus 1 as well, would also allow. All right, so the main fact of life is these are marvelous gates. They do as well as the golden ratio in many respects does for the ordinary rotation. Okay, now there's some feature I want to discuss, this navigation, because that's a part that computer scientists discovered. This, the other aspects were naturally evolved out of the work of Lubotsky, Phillips, and myself. But there was something they discovered, these 3 computer scientists and many following them, in particular Ross and Selinger, is once they wrote down what the entries in their Clifford and T, they looked how to navigate quickly. How to navigate means to take an element G and find a short path to it in terms of the T count. And they found heuristic algorithms, and by the way, when it comes to algorithms, I don't care about proofs. The proof of the pudding is they implemented it and it works. And you never argue with success. So at first I was a bit suspicious, but they ran it. They have a lot of heuristic assumptions along the way, and if it works, and it absolutely works, it finds short paths. Now, there's something a little funny here, and it's a bit circular. In the algorithm, and it's not difficult to adapt the algorithm to all these golden gates, is based at some moment on assuming that you can factor a number quickly. Okay, so there's a very beautiful and unsolved problem, at least in the public domain, if I give you a large number n, can you factor it quickly? And crypto systems, RSA, are based on the false news, I think, that factoring is hard. People like you to believe that factoring is hard. There's no evidence factoring is hard. The fact that nobody's factored doesn't mean that it's in principle hard. It means that in this world it's hard because, and if somebody knows how to do it, they're not going to show you. So in the public domain, it's considered to be difficult. But in mathematics, all the problems we work on have not been solved before. So if we say because nobody succeeded, we're not going to do it or try to do it, you have to have a belief. You have to believe what's true if you're going to put something and put your whole life and try to prove something. So you have to have a belief of whether factoring is hard or not. And my personal belief is that factoring is easy. But I learned something from this quite seriously. Firstly, one reason that quantum computing, why people are so eager to build a quantum computer, is that with a quantum computer, you can factor quickly. That's an algorithm of short. So if anybody ever builds a quantum computer, all these RSA schemes are bust. So it's of great interest to many people to understand if you can build a quantum computer. And that's one of the remarkable things that a quantum computer is known to do well, but we don't know whether a classical computer can do it well, but I believe you can. Funnily enough, in building this this gate, in order to show that they can navigate with these kind of golden gates, they need at some point to assume that you can factor quickly. This is not a disaster. This is a red herring. Because what happens is, at some point you're trying to solve a Diophantine equation to find a short path. And when you try to solve that equation, you try a factor. So I told you they implemented this algorithm. They actually implement it, and they try factor. And if it fails, then they just start again. And after a few tries, they might not find the shortest path, but they might find the second or third shortest path, which in practice will be good enough because that's all you need. Now, their algorithm only navigates to a diagonal element in the matrix. It uses, so if you want to, in the group, so you are looking at 2 by 2 complex matrices, unitary matrices of determinant 1. You want to find a short path with these kind of golden gates to a small neighborhood of some guy. If that guy is diagonal, so you start off with the diagonal guy and you want to navigate from the identity to there, you can, the heuristic algorithm will do that with this factoring, assuming you can factor quickly. And that, as I said, is implemented. I became very interested in this because I thought, why are they only able to navigate to diagonal? Doesn't make sense to me. We should be able to navigate to anything. By the way, you can then navigate to anybody with a path that's 3 times longer than it should be, because you can write any matrix. You can also do anti-diagonal. So you can write any matrix in Euler angles and write it as a product of 3 matrices, and then the length of your approximation would be 3 times longer than we know it should be. So it's still, other than this factor of 3, it's very good. But I was able to show, and this was a shock to me, and this is in this paper, that if you want to navigate to the general element, this is NP complete. So this is a problem with, okay, I'm not crazy, you know. I believe you can factor quickly, but I don't believe you can, I don't believe P equals NP. You can't solve every problem quickly. Factoring is very structured. So it turns out that if you want to navigate to the general guy here, we have an argument in this paper which reduces that problem, which looks like a very simple problem in 2 by 2 matrices. The most difficult NP-complete problem, satisfiability, can be built into this problem. In fact, something called the knapsack problem. So that you can't find the shortest path to a non-diagonal guy unless you prove P equals NP. So this is a lesson here, and I will end with that lesson. But I just want to tell you what one ingredient, so I don't have time. I think I have 50 minutes, I must stop now. So I just wanted to, and I'm here the whole day, and I'll be happy to explain any aspect of this that I'm able to. But I wanted to point out 2 things. One is the fact that these cover optimally in the way that I told you that with balls and boxes that random points do, makes use of something called the Ramanujan conjectures for modular forms of arbitrary weights solved by Deligne. So there's a great pleasure using something very serious in a practical way like this. That is not used in the algorithm, it just proves that these points cover optimally. The fact that they cover, not with an algorithm, but the fact that they cover makes use of that at a critical moment. And then let me end with this one point which was a shock to me and should be in all textbooks and isn't. So I told you that I believe you can factor quickly. So if you give me a number n and you ask me what are its prime factors, or maybe n's just got 2 prime factors, but I'm going to allow n to have many prime factors right now, and you want to factor, if you give me the factors, I can check in the number of digits whether that's correct. So I can check the answer quickly, but if I give you n and I ask for the factors, we don't know how to do that quickly. I don't believe that's a difficult problem. I think one day you will pick up the newspaper and some young person like you, or maybe from Siberia, young high school student will have factored quickly. And again, the proof will be in that you can assume anything you want. If you're given a large number and you find the factors and you're making all sorts of assumptions along the way, as long as it works, nobody will argue with you. But suppose you change the problem a tiny bit. And this is the thing that was the source of this NP completeness. Instead of saying, I give you a number n, and I ask you for its factors, I give you a number n and I give you alpha and beta. I give you 3 numbers, which are large numbers, and I give you them in base 10. So the number of digits is the complexity of the input. And I say, is there a factor, are there factors, can you solve the equation x times y equals n, with x in between alpha and beta? So I give you 3 numbers, n, alpha, and beta, and I say, question, is there a solution to this with x times y equals n, and x is in the range alpha, beta? So that seems like an easier problem if you were going to be searching. That's NP complete. That problem is hard as any NP problem. So if you can solve that, you've completely changed the world. So I have no doubt that you cannot do. And that's kind of surprising. So when you want to factor n, my belief is you can do it quickly. But if you put in a Diophantine approximation, which is what we're doing here, on top of that, so the moral of the story is if you have a linear equation in integers in fixed dimensions, that can be solved quickly. That's a theorem of Lenstra and used in this algorithm. But if you have a quadratic equation and an inequality, so a linear program for quadratic Diophantine equation, that's NP complete. And it's a good lesson to learn from that we still don't understand the quadratic equation. Thank you.